two projects. In this video, we are going to explain about the project that is AutoBDA Model Driven Reference Architecture for Automated Big Data Analysis Framework. So before getting into the execution, first let us understand what is the project. So in this project, the main is to deal with the data. And that data is generated from the IoT devices. So what is this IoT? IoT is Internet of Things, or we call it in short as IoT. It has been growing at an incredible pace. Today, we have millions of devices like environmental sensors, wearable health monitors, and smart consumer devices. They constantly generate enormous amount of data. So this data carries valuable information. For example, environmental sensors, they can help us to detect natural disasters early. Health monitoring devices can track patients' vital signs in real time, and smart city devices can support better resource management. However, dealing with this all data is not easy. Traditional machine learning methods and simple big data analysis approaches struggle when the data becomes too large or too complex. They often become slow, require a lot of computing power, sometimes fail to adapt to changing conditions. Big data analysis itself is a complicated process that involves multiple steps, and it often needs extensive knowledge and time to produce meaningful results. Because of these limitations, industries and societies are not fully able to take advantage of the massive generated data by the IoT devices. So, this is a major challenge because the amount of IoT data continues to grow every day. To meet the goals of the modern systems like Industry 4.0, which focuses on smart factors and automated processes, and Society 5.0, which aims for highly connected, human centric societies, we need faster, smarter, and more scalable ways to analyze this data. The ultimate goal is to have a data analysis methods that are efficient, accurate, and able to provide actionable insights quickly. Here, even though there have been many advancements in big data analysis and machine learning, most of the current solutions are limited to very specific domains. This means they work well for one type of data or application but cannot easily adapt to different types of problems. They also lack flexibility and inclusivity, which makes it difficult to create systems that can automatically adjust and provide services in a wide variety contexts. So, because of this, processing large amount of IoT data efficiently and getting timely actionable insights is still a big challenge, as amount of data generated by IoT devices keep growing every day. There is an increasing demand for analysis methods that are faster, more accurate, and can scale to handle this growth. To achieve the goals of Industry 4.0 with a focus on smart automated industries and the Society 5.0, which aims for human centric, highly connected societies, it is crucial to have approaches that can overcome these challenges. So, to overcome with all such issues, this project designs an automated big data analysis framework for AutoBDA, which is designed to handle and analyze very large data sets that are generated by IoT devices efficiently. In this project, the focus is on predicting earthquakes, so the system is built to process earthquake related data from various sources. And to do this effectively, the system uses distributed computing framework like Hadoop and Apache Spark. These frameworks allow this data to be processed in parallel across multiple machines, which makes handling massive data much faster and more efficient. So this approach addresses the limitations of traditional machine learning models, which often struggle when dealing with a very large or complex data sets. And at core of this project, so the project uses logistic regression for main predictive model. As a main predictive model, it analyzes historical earthquake data and forecasts the magnitude of future earthquakes. The system is designed to be modular and fully automated, which follows a clear stages, that is data pre-processing, model training, evaluation, and deployment. So during training, that is during pre-processing, the system handles missing data, converts categorical information into numerical form, and splits the data into training and testing. This ensures the model is trained properly and performs reliably. After training, the model performance is evaluated using RMSE and MAE. RMSE is root mean squared error and MAE is mean absolute error. So this measures how close the predicted earthquake's magnitude are to the actual values. Low values indicate better prediction accuracy. And to further improve the performance of this project, here we have incorporated random forest and gradient boosting algorithm. So the system has been upgraded to use more advanced machine learning algorithms. In addition to the traditional logistic regression model, random forest and gradient boosting, that is GBT tree algorithm, have been incorporated. Random forest, it improves the prediction accuracy by reducing errors compared to the logistic regression, while gradient boosting goes a step further, providing even lower errors and more precise predictions. And here, to make the system more practical and user friendly, a web interface has been developed using Flask. This allows users to easily input new data and get predictions of earthquake magnitudes using the trained models. Overall, this extension enhances both the accuracy and also usability of the system, which makes it more robust, reliable, and accessible solution for automated earthquake prediction using big data. Moving on to the implementation, to implement this project, we have followed steps which are mentioned in the flow of work. So first, we have imported all the necessary Python and Spark libraries that are needed for data processing, machine learning, model building, and also for the user interface purpose. Then comes initializing Spark session. So here we start a Spark session, which allows us to use Apache Spark's distributed computing capabilities. So this helps us to process large data sets efficiently across multiple nodes or core. Then comes data collection. So the first step is to gather earthquake related data from various global sources. This dataset includes important parameters such as earthquake, magnitude, intensity, location, alert levels, and other environmental features. Collective comprehensive data is essential to train predictive models accurately. Then comes data exploration and visualization. So once the data is collected, it is analyzed to understand its structure. We check for missing values, distributions of features, and correlations between different parameters. Visualization tools like histograms, bar charts, pie charts, and line plots helps in understanding the trends and relationship in the data set, which makes it easier to prepare the data for modeling. Then comes data pre-processing. So in this step, the data set is clean and prepared for machine learning models. Missing values are handled and categorical features such as alert levels are converted into numerical values. Selected features are combined into a single feature vector that machine learning models can process. The dataset is then split into training and testing to ensure that the models are trained effectively and can be stored on the unseen data. That is, they can be tested on unseen data. Then comes model training. So here in this step, the pre-processed trained data is used to train multiple regression models to predict earthquake magnitude. Here we have used linear regression, random forest, and gradient boosting tree algorithm. And all those models are evaluated using this RMSE and absolute error, that is mean absolute error. And then we will be selecting best performing model. Coming to prediction. So here, once the best model is selected, it can be used to make predictions on new data, that is new earthquake data providing users. The new data is pre-processed using the same transformations applied to the training data set, ensuring consistent results. Then comes model deployment. So the trained model is integrated into a Flash-based web application, allowing users to input earthquake-related parameters online. The system then predicts earthquake magnitude, making it accessible and practicable for users to analyze potential earthquake risks. So this is how we have implemented the project, and these are the algorithms used. Last two are the extension models. So to implement this project, basically we need hardware and software requirements. In hardware, we need operating system of Windows, processor of 5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. And software requirements are application of Python, front-end framework of Flask, back-end framework of Jupyter Notebook, database of SQLite 3, and front-end technologies are HTML, CSS, JavaScript, and Bootstrap 4. So this is all about the overview of the project. Now let's execute. To execute, let's open the code folder that contains source code files. These are the source code files of the project. In this folder, we have the data set. This is the data set that is used to train the models for predicting earthquake. So this is the data set used to train the ML models. So this data is loaded into Notebook by using Spark. So this is the model that we will be predicting. This is the variable that we will be predicting in this project. And these are all the independent features. Close this. And these two are the test data files that we will be using in the front end. Get back. This is the static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap files, which are important for the visual appeal. And this is the templates folder. This folder contains all the HTML pages used in this project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. And this is notebook file. It's a Jupyter notebook file which contain a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells. And in this notebook file only, we will be loading the data, we will be initializing Spark session, and then we will be training the models. This is the main.py file. So this file contains information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in HTML templates. So this is the run.bat file. Instead of executing project through command line interface, we have created this Windows batch file. So now we need to double click on it to run this main.py file. So double click on it, click on run. So here you can observe main.py file is compiled. So this command, it will execute Python script and perform a runtime check for any syntax errors or logical issues. And after running this main.py file, Flask framework will host the application locally at the default address, which will be the local host and the port unless configured differently. So just wait for a while. So at this address, application has been hosted. This is the local host and this 5000 is the port. Now copy this local link provided by the Flask framework. I have copied it and paste it into any web browser. I prefer Google Chrome, so I will paste it in that.
So paste the link here. Now click on enter. This is the web page of the project which is displayed in the browser, and this is developed using Flask framework. Now click on register to get registered. Enter all your username and the password. I mean username, password, email address, mobile number, and address to get registered. I have already registered, so I'll directly log in. Click on home, click on user login, give your username and the password. Click on login. We have logged in successfully and redirected to prediction page of the project.
So here you can see browse files link, right? I mean browse files button, right? We're supposed to click on that for uploading the test data for getting the predictions of earthquake. So click on browse files. Now select test data to upload. So select it, click on open. And now we need to click on upload data to get the predictions. Before uploading it, let's see what do we have in the test data file. So let's open it. So these are the inputs that we will be giving. So these are the number of parameters that are total 24 will be giving us the input and total 15 test cases. So these are different variables of earthquake. Let's get back to the application. Now click on upload data. So this given information, it will be pre-processed at the backend. It will be fed it to the train model, and then train model will be giving us a prediction, predicting the earthquake's magnitude. So just wait for a while. So here we got the prediction for the sample one. This is the sample one that we have given. For this, here it is predicting it as 6.8 magnitude. So this is the 6.8 magnitude where the earthquake will be happen. So same we have for sample 2, sample 3, here we have 6.5 Richter, sample 4, for sample 5 it is 6.6, and for sample 6 it is 6.8, for sample 7 it is 6.6, for sample 8 it is 6.6, and then for sample 9 it is 7.3. Accordingly, we have for all the samples that we have given. So total we have given 11 samples and it is giving 11 predictions. And average magnitude it is 6.83 and highest magnitude is the 7.5 magnitude. Now let's check with the service access time graph. So click on that. Here on x-axis we have number of requests, that is number of files we have uploaded, and on y-axis we have access time. So it is giving predictions in how much time. So here we have this prediction. Here we have this point. Now let's upload one more file. So click on drop your file here. Let's upload this one. Click on upload data. So here also we have multiple samples given. And for all the samples that we have given, it is giving the prediction. Here also we have average magnitude to be 6.83, 7.5 as the highest magnitude. And click on service access time graph. Here, if you observe on x-axis, we have number of requests, and on y-axis, we have access time. So this is the access time for the first file we have given, and this is the access time for the second file we have given. Now click on log out. So in this way, by using big data, we can load a huge amount of data very quickly, and we can do predictions accurately without giving any inaccuracies. And here we have predicted earthquake data, which is the huge data. We have predicted magnitude of it. So this is all about the project.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.